As we saw in the last couple of videos, we were using the alumni data set, alumni giving data set, to try to make some kind of inference. So I'm trying to understand how alumni give back to their universities. So we looking at data and trying to use that to help understand and infer and predict what the alumni giving rate is given different independent variables. So in order to actually use regression for inferences, there are several assumptions surrounding the error terms, those epsilons from the regression model. They are: the errors are normally distributed with a mean of 0 and a constant variance. So there's three parts to that one, right? First, that they're normally distributed. Second, that they have a mean of 0. And third, that the variance of those error terms is constant. Then the other assumption is that the epsilons, the error terms, are statistically independent of one another. So in cases where they may not be statistically independent of one another is some time series stuff, which we'll get to later. So in order to know whether or not regression can be used for inference, we should do some analysis around these residuals or error terms, since they have assumptions. So for our purposes, we will create scatter plots involving the residuals. Remember, the error term is the actual minus the predicted. That's the y sub I minus the y hat sub I. Or we might standardize those residuals to see what they look like. We want to examine the residuals on the y-axis, the vertical axis, against the predicted values y hat sub I, and each of the independent variables x sub I. So let's do a scatter plot and see what it looks like. So what would be something that we would want to show up in the scatter plot? So here's a good pattern. This time we're looking at the predicted y hat on the x-axis, the error term, the residual, on the y-axis, and we see this is a good pattern because they look like there's about the same number above the 0 line as there are below it. So it looks like they're centered around 0, the mean of 0. It looks somewhat normally distributed, or at least symmetrically distributed, which is what we're looking for. And there doesn't appear to be any issues with the variance, which means that the differences between the highs and lows doesn't seem to vary as we look through these different parts of all the y hats. Right? So this looks like a good pattern. So then what does a bad pattern look like? Because it's just as important to be able to recognize a bad pattern as it is a good pattern. So here are 4 different bad patterns. The first one up in the upper left-hand corner, labeled A, looks like a shotgun blast. Right? What's going on here is that we probably do not have constant variance across these residuals, right? So down here, they're varying just a little bit. Out towards the big part, not so much. There's a lot more variance. So that's probably violating one of our assumptions. So there are different ways to handle that, right? B, we see this U-shape or V-shaped kind of pattern to the residuals. This tells me that that linear regression probably is not a good idea. Instead, some kind of non-linear might be good, or I might try to transform the variables to make them more linear. So our functional form of linear is probably not the best thing going on. And then so down in C, we see a bunch of stuff down here, or it looks like there's more error terms that go kind of out of whack up high, and a bunch of stuff down low. So it looks like a skewed kind of distribution. So again, we might be able to transform those variables to get us to something that would be useful. And this next one looks like it must be time series because we have a line plot, so these must mean something, right? Remember when we have a line plot versus a scatter plot. what we're doing is, yeah, this is a little t, so that represents time. We when the x-axis is something that is relevant in terms of order, then we can connect the markers with the line segments to come up with a line plot. So to me, this looks like we've missed seasonality. It looks like maybe quarterly data, first quarter down here, second quarter, third quarter is the highest, fourth quarter is the lowest, right? Looks like the fourth quarter is always the lowest, right? Third quarter is always the highest. So we've missed something. We could add in dummy variables for seasonality and probably take care of that. So let's say that we feel like the assumptions are going to be met. We'll test them in a little bit. So we want to have a hypothesis test for overall model significance. We saw this before. We looked at this and we looked at the significance F in the Excel output in the alumni giving. The hypothesis test is that the beta 1 is equal to the beta 2, which is equal all the way up to the beta whatever, is equal to 0. The alternative hypothesis is at least 1 is not equal to 0. So we conduct an F test using the F distribution. For us, we look at significance F in that ANOVA table at the top, and we see that a small p-value would reject the null, right? And that would tell me that overall the model is statistically significant, so that at least one of the betas is not equal to 0, so it should stay in there. It doesn't tell me which one, so then we have to move on to individual variable significance, which we did. We looked down at the coefficients for each of the independent variables, each of the explanatory variables, and that hypothesis test is the null is beta sub I is equal to 0, alternative beta sub I is not equal to 0. So a small p-value means reject the null, which means that I believe the alternative is probably true. So that would mean that the coefficient is not equal to 0, so we think we should leave it in. If we get a large p-value, that gives credence to the null hypothesis, meaning that we think that coefficient really is 0. And if it's really 0, then when you multiply the coefficient times the variable, it will be 0. So we should just take it out of the model. That's why we took out the class size when we were looking at the alumni giving example. And then the other thing we're interested in, that we're also interested in, is the coefficient of determination, which is the R-squared value. So when you add an additional independent variable to the model, the R-squared will either stay the same or go up, regardless of the statistical or practical significance of the additional variable. So I could add in weather data, how many blue moons we had in the past year, something crazy, right? And the R-squared would either stay the same or go up. So instead, when we look at multiple regression, many times we look at the adjusted R-squared. And what it does is it adjusts the value of the R-squared, the coefficient of determination, based on the number of independent variables as well as the sample size. And then we also went ahead and looked at categorical explanatory variables in the alumni giving, where we looked at the U.S. region. Right? So many times we looked only at quantitative variables, but sometimes we have factors that might be categorical. They could be binary, a yes, no, a male, female, this one or that one kind of thing, on, off. And in multiple categories, cash, credit, PayPal, check, right? So we saw multiple categories when we looked at U.S. region. So we handle categorical variables by creating dummy or indicator variables, where we say x sub I is equal to 1 if it's yes, 0 if it's no, for a yes, no. We could also talk about if it belongs to that category as well. So let's see. We have an example where we might have risk of stroke. This is actually your Excel assignment for this unit. So the American Heart Association collected data on how age, blood pressure, and smoking relate to the risk of stroke. Risk is the chance of having a stroke in the next 10 years. And one of the data in there is called a smoker. So let's go to Blackboard and look at the Excel assignment for, let's do March 13th. It's a Monday. So we're going to be looking at the stroke data. So I'm going to go ahead and download that. Open it up. Bring it over here so you can see it. Something like that. Make it bigger. Right. So we're trying to help predict risk of a stroke given someone's age, their blood pressure, it looks like the top number, and whether or not they are a smoker. Notice this is a no or a yes, right? So if I tried to do a regression on this text, it would not work. Regression needs numbers. So what we need to do is create a dummy variable that is a 1 if it's a yes, like in row 5, and zeros if it's a no. All right. So we can do this. Let's call it smoke dummy. All right. And we can say if this is equal to yes, return a 1, otherwise return a 0. And then we can copy it all the way down, and we see you have a 1 for a yes, 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 no, yes, right? So now we have a dummy variable that we can use in addition to these guys, right? But remember, in order to do the multiple regression using that, this column, E, has got to be next to those columns. You've got to have it contiguous in the regression. So let's go back to where we were. Right, so that's a yes-no, a simple kind of categorical. For more complex categorical variables, like we saw in the alumni giving example, for K levels we need K minus 1 dummy variables. We had 4 regions, so we needed 3 dummy variables. And again, the base level is the one that's represented when all the dummy variables are equal to 0, the one we leave out. So we did that with the alumni giving the last time, right? So that was last time. So we created 3 different regions: Northeast, South, Midwest, and then West was our base. So when it was all zeros, we did that. If you don't do K minus 1 dummy variables and try to run a regression, you get some # num, and it doesn't complain necessarily, but the results look weird and are incorrect. So you need to only use K minus 1 dummy variables.